In this video, we're going to check out how to verify solutions to differential equations. The method is we're going to plug the proposed solution into the differential equation and check whether or not the two sides are going to match. Example 1. The equation is x y prime plus y is equal to x cubed. And the proposed solution is y is equal to x cubed over 4 plus 1 over x. In order to plug the y and its derivative into the equation, we have to find the y prime here, which is not provided. And to do the derivative for these two terms, we notice that both of them can be put into powers. The 1 over x is actually x to the negative first. So now we can apply the power rule. Namely, you're going to bring the exponent in front and then reduce the exponent by 1. So the first term, you bring the 3 in front, you get 3/4, and then reduce the exponent by 1, you get x squared. For the second term, you bring the -1 in front, you get a minus sign here, and reduce it by 1, you get x to the negative second power, which is 1 over x squared. Now we can plug the y and the y prime into the equation. And we can do the distribution. And we combine the like terms. And then we're going to get x to the third, which is the right-hand side. So we just confirmed the two sides, they match. Therefore, the proposed function, it solves the differential equation in its domain. Example 2. The equation is y to the fourth derivative minus 16y is equal to 0. And the proposed solution is y is equal to sine 2x plus 3 times of cosine 2x. In this case, we do not have y prime, y second derivative, the third derivative. But in order to find the fourth derivative, we have to find the first 3 derivatives of y. So anyway, we have to start with y prime. And then we notice that both of these two terms are actually combinations of trig functions and polynomial 2x. So therefore, we have to use the chain rule to figure out the derivative. Recall that the chain rule is for composition of two functions. You're going to do the dy du and then du dx. So in this case, if we set u as 2x, then we know here we're going to get sine u and here we got cosine u. So we can use the chain rule in this way. And then we know the derivative of sine is going to be cosine. Du dx, when u is 2x, is going to be 2. And for the second term, the derivative of cosine is going to be negative sine. Du dx again is going to be 2. So finally, we got y prime is going to be twice of cosine 2x minus 6 times of sine 2x. We can do the same thing for the second derivative. In particular, when you do the derivative of cosine 2x, you're going to get negative sine 2x. And for the inner part, the 2x will give you an extra 2 here. That's why you're going to get negative 4 times of sine 2x. Similarly, for the sine 2x, its derivative is going to be cosine. And the inner 2x will give you another 2. That's why you're going to get the 12. So we understand by using the chain rule, we can get y triple prime and y to the fourth derivative in a similar way. In particular, each time you're going to get the extra 2 from the argument 2x. So that's why you see the coefficients are going to be doubled each time. And another issue is whenever you do the derivative for cosine, you have to change the signs. Finally, we can plug the derivative and the y into the equation. Once again, we need to do the algebra, and we can cancel the like terms and get 0. So again, we verified that the left-hand side and right-hand side, they are the same. Therefore, the proposed solution, it is a real solution to the differential equation. Example 3. The equation is x squared y double prime plus 5x y prime plus 4y is equal to 0. And the proposed solution is y is equal to x to the negative second power times natural log of x. And we understand the domain for the y is going to be x is greater than 0. For this function, we notice that the y here is a product of a power and the natural log. So to do the derivative, we have to use a product rule. And the product rule says, if you do the derivative of a product, you're going to take the derivative for a factor at a time. You're going to go through all of the factors. And then once you finish them, you're going to add them up. So with 2 factors, we're going to get 2 terms here. And you just use the power rule and the derivative of log. You can get the first term, you bring the -2 in front, reduce exponent by 1. You're going to get -2 times x to the -3rd, and then natural log of x. And for the natural log of x, its derivative is going to be 1 over x. So times x to the -2nd, you're going to get x to the -3rd. Now we need to find the y double prime, and you're going to get the product again. So you're going to use a product rule again. So we're going to do the derivative for the first term times the second term, plus the first term times the derivative of the second term. And then you have to also do the derivative for the second term of the y prime by using the power rule and the derivative of natural log. We'll get this will be the y double prime. And we combine the like terms, we get it's going to be 6 times of x to the -4th power times natural log of x minus 5 times of x to the -4th power. And now we're ready to plug the y and its derivatives into the equation. And we notice that the x squared and x can be distributed into the parentheses. And you're going to get all of the powers because we have x to the second and x to the -4. They have the same basis, right? So all of these powers, they can be combined. We know we keep the x as the base, we add the exponents. And after you do that, you're going to see all the powers will be x to the -2nd power. Because here 2 with -4. And here x is x to the first with -3. So all of the powers are going to be x to the -2nd. And then we put the coefficients here. And then you can see the cancellations. You have 6 minus 10 plus 4, this many natural log of x, which is 0. And the constants will also be 0. So we end with 0, which is right-hand side of the equation. So we know the 2 sides, they are the same. Therefore, the proposed function is going to solve the differential equation. Example 4. The way this problem is proposed is different from the first three examples. So for this one, we're not sure whether or not this function y is equal to t plus 1 times e to the negative 2t is a solution or not. We need to make a decision. But the strategy is going to be the same. We simply plug this into the equation and say whether or not it's going to make the equation true. And in order to do that, we need to find the derivatives. And because here we have a product of a polynomial and e to the negative 2t, so we have to do the product rule. So once again, this is the product rule. We're going to do the derivative of the first term times the second term, and then plus the first factor times the derivative of the second factor. And easily, we can figure out the first factor's derivative, which is going to be 1. For the second factor's derivative, we have to use a chain rule again, because e to the negative 2t is a composition of the exponential function and the negative 2t. So by using the chain rule, we'll get the derivative for the second term is going to be negative twice of e to the negative 2t. And then we can factor the e to the negative 2t and simplify the y prime as negative twice of t minus 1, and then times e to the negative 2t. And we can do the same thing to get the y double prime. In particular, you notice that the y prime is also a product, so we have to do the product rule. And when you apply the product rule, you once again have to figure out the derivative of e to the negative 2t, which is already found in the first step. So we just combine all of the like terms, and we get the y double prime is going to be 4t times e to the negative 2t. We still need to get the y triple prime, and that can be obtained from the derivative of y double prime, which is also a product. So we have to use a product rule here. And once again, you have to find the derivative of e to the negative 2t. And after the simplification, we will say the y triple prime is going to be negative 8t plus 4, and then times e to the negative 2t. And now we're ready to plug the y and its derivatives into the equation. We'll say there's a common factor e to the negative 2t, which can be factored out. And then you collect all the coefficients. You're going to end with 8 times of e to the negative 2t. This time, we notice that it's not going to be the same as the right-hand side of the equation, which is twice of e to the negative 2t. Namely, the left-hand side and the right-hand side, they are not equal. This means the function proposed here is not a solution to the differential equation. That's all for this video. Thank you.